Look up at a clear night sky, and it feels incredibly peaceful. The stars seem still, quiet, and permanent. But to understand how those stars got there, we have to mentally collapse that entire sky backward, all the way to a single chaotic point. Imagine taking all the matter and energy in the universe and crushing it into an unimaginably small volume. This single, tiny ball had infinite temperature and infinite density. This diagram represents our universe's timeline. Right here at the beginning, 13.7 billion years ago, that tiny ball exploded violently. As it rapidly expanded, the extreme energy began converting into actual physical matter within fractions of a second. It took about 300,000 years for the extreme heat of that explosion to subside. The temperature finally dropped to 4,500 Kelvin. That cooling allowed the very first atoms to form, and the dense, glowing fog cleared. The universe became transparent. The Big Bang simultaneously generated space, time, and matter, expanding the universe's physical boundaries from the inside out. We know this expansion is real because we can still observe it today. In 1920, astronomer Edwin Hubble provided the first concrete evidence that the galaxies around us are actively moving further and further apart. You can picture this like a balloon with dots drawn on it. If you inflate the balloon, the rubber stretches, and every single dot appears to move away from every other dot. The universe operates on a similar principle. But there is a catch to this analogy. The space between the galaxies is increasing, stretching out across the cosmos. The galaxies themselves, however, stay the exact same size. They do not inflate along with the space around them. As that space continued to expand and cool, gravity went to work. Between 5 and 6 billion years ago, massive accumulations of hydrogen gas began to gather, forming vast, localized clouds known as nebulae. These nebulae were not perfectly uniform. Slight variations in density allowed gravity to pull the gas into tighter, heavier clumps. As these clumps grew, the friction and pressure inside them built up until they ignited into the very first stars. Without the immense outward push of the universe expanding, gravity would not have had the raw materials or the isolated pockets of space to sculpt those early gas clouds into celestial bodies. That same process of gravitational collapse eventually formed our sun. In its youth, the sun was surrounded by a massive, slowly rotating disk made entirely of leftover gas and microscopic dust. Inside that rotating disk, particles of dust were constantly colliding. Friction caused them to stick together through a process called cohesion. Over time, these tiny grains built up into larger, jagged rocks known as planetesimals. Once a planetesimal gets large enough, it generates a meaningful gravitational pull. This starts a chain reaction called accretion. The largest chunks act like vacuums, pulling in more and more surrounding debris until they grow into full-sized planetary bodies. About 4.6 billion years ago, one of those growing bodies became the Earth. But it looked nothing like the world we know. It was a barren, incredibly hot rock, wrapped only in a thin, fragile layer of hydrogen and helium. A violent, high-speed bombardment of cosmic debris physically hammered the Earth into its spherical shape over millions of years. All of those high-speed impacts generated massive amounts of thermal energy. Because of the sheer volume of collisions during its early formation, the entire planet remained in a partially molten, liquid state. This extreme heat was sustained by massive events, including a colossal collision with another protoplanet. That specific impact spiked Earth's temperature again, ensuring the rock remained a churning liquid. Being trapped in this molten state allowed a mechanical sorting process to occur. Scientists call it differentiation. Inside a liquid planet, gravity pulls on materials differently, depending strictly on their density. The heaviest, densest elements, like iron and nickel, were drawn straight down. They sank through the molten rock and pooled at the very center to form the planet's core. Meanwhile, the lighter, less dense materials floated upward toward the surface. As the outer edges of the planet finally began to cool, these lighter materials hardened, solidifying into the rigid crust and the lithosphere we stand on today. The extreme heat and subsequent cooling were the exact physical mechanisms required to sort out the rock. giving Earth its distinct layered structural foundation. Earth now had a solid crust, but its thin original layer of hydrogen and helium was quickly blown away by intense solar winds. That left the planet with a blank slate for a new atmosphere. The raw materials for that new atmosphere were locked deep inside the Earth. Through a process called degassing, the intense heat of the interior forced trapped gases and water vapor outward, where they pushed their way to the surface through constant volcanic eruptions. Those early volcanoes continuously pumped a specific cocktail into the sky: massive amounts of water vapor, nitrogen, carbon dioxide, methane, and ammonia. As the rock beneath these thick clouds continued to slowly lose its heat, the surrounding air temperature dropped. Eventually, it became cool enough for the massive volume of atmospheric water vapor to condense into liquid rain. This chart illustrates the turning point. As surface temperatures dropped, the volume of liquid water exploded. Roughly 4 billion years ago, centuries of torrential rain began pooling into massive depressions in the crust, giving birth to the first oceans. The internal cooling of a solid rock directly produced a dynamic, fluid environment on its surface, setting the exact conditions required for the next phase of the planet's evolution. Down in those newly formed oceans, about 3.8 billion years ago, simple chemicals began reacting. They formed complex organic molecules that grouped together and achieved something remarkable: the ability to duplicate themselves. We can actually trace this back in the fossil record. Deep inside ancient rocks, we find microscopic structures left behind by the very first single-celled organisms, similar to modern blue-green algae. Over the next billion years, these simple organisms slowly developed the ability to photosynthesize. As they consumed sunlight and carbon dioxide, they released oxygen as a byproduct, triggering the oxygen revolution. This diagram shows how that timeline played out. For millions of years, early life pumped oxygen directly into the water. Around 2 billion years ago, the oceans reached absolute saturation. The excess oxygen spilled off, rapidly flooding the atmosphere. Biological activity reconfigured the chemical makeup of the air. This cooling ball of magma had successfully generated its own water, an oxygen-rich atmosphere, and a stable biosphere. The 13.7 billion-year timeline integrates the Earth's formation into the universe's original expansion, a continuous sequence of cooling and chemical creation.